Now we are at the last session of the today. I think our last presenter has been waiting for a long time. So I believe we saved the best for the last. So now can we invite Koen van der Mo? Sorry for my pronunciation. Principal researcher, PhD student, DMV, to give a presentation on the exploring changes to operator roles and tasks in transitioning towards increased supervisory control of autonomous collision avoidance system.
Good afternoon. My name is Koen van der Merwe. I work in DNV, the Group Research and Development section. I also do a PhD at the University of Southeastern Norway, and the topic of today is exploring operator tasks in increased supervisory control of autonomous collision avoidance systems. The context of this work is the increased use of technology in shipping, especially, of course, autonomous shipping, which purports to create increased safety and efficiency of operations. But still we see the use of either remote or local supervision by a human supervisor with the option to intervene if needed. Increased automation and the increased use of technology in shipping can also be seen as an increase in complexity. Complex systems are challenging for humans to understand and supervise. This has been named as the Automation Conundrum, which is the more automation is added to a system and the more reliable and robust that automation is, the less likely that human operators overseeing the automation will be aware of critical information and able to manually take over when needed. However, some researchers have proposed that the idea that, well, what if we make such a complex system, the internals of this complex system visible to the user? This is called automation transparency. So if we make visible to a user what the system is thinking, how it is analyzing it, why it is performing certain actions, and what it will do next, then maybe this will help a human supervisor understanding this system. And maybe this is then a so-called free lunch, a way out of this automation conundrum. This is the overall topic of the PhD, and it's also in part discussed in the paper presented here, is to better understand this role of automation transparency in the supervision of autonomous vessels. So supervising an autonomous system can be seen in itself as a complex task. So a complex system can also be seen as a very capable system. It provides many advantages. It can perform complex tasks. However, as mentioned, the supervision of a complex system can also be seen as a complex task in itself, especially if we take into consideration that the world is imperfect. So probably the design of this complex autonomous system will be imperfect. Therefore, it means that there will be tasks that are unforeseen during the design of the system that a human supervisor is left to cope with. In addition, there will also be tasks that were maybe too difficult or too challenging to implement in this complex system. This means that a human supervisor supervising such a system is left with monitoring the status of this system and, if needed, to take over manually. This is what I wanted to explore further in this work. By exploring operator tasks in collision avoidance. I wanted to systematically map and assess performance requirements for two scenarios. First, baseline, a conventional collision avoidance situation also called operator exclusive, and another scenario which is called supervision, in which an agent is introduced that is able to perceive information, analyze this information, make decisions and take actions by itself in the context of collision avoidance maneuvering. The human is here to supervise this system and to initiate fallback if needed. What I set out to do was to create a very large Excel sheet, if you will, but there is quite a structure to it, and I will guide you through this. So the Excel sheet here, the spreadsheet, is organized around the collision regulations, and the collision regulations provide both the rules but also the scenarios in which the collision avoidance maneuvering is analyzed. So I had these two cases, the baseline and the supervision case, and for each of these cases I performed a so-called cognitive task analysis to identify the performance requirements. The input to this Excel sheet were the collision regulations themselves, because the co-regs describe in a fair amount of detail tasks to be performed, the task responsible, and information and equipment used and needed. In addition, I also reviewed procedures from a ferry operator. I performed 9 interviews with navigators whilst they were on duty on the bridge. And at the same time, I performed observations in collision avoidance maneuvering. All this fed into this spreadsheet. In addition, I have also executed a number of workshops with independent navigators to validate the content of this work. So as mentioned, the core regs provided the scenarios. I performed a cognitive task analysis, meaning I identified the key tasks to be performed, mostly focusing on the decision-making task and the information processing task, so the cognitive elements, the information requirements to execute these tasks, identified the one who is responsible for executing these tasks, and any time requirements that could be set on this task. This led to a so-called performance requirement, which is a description of basically these elements which I just described: who does what, when, and how. In the right side of this spreadsheet, you can see that I did this, so let's say, a thought experiment, which I assumed the presence of a collision avoidance system capable of performing collision avoidance tasks, and a supervisor supervising this collision avoidance system. And I asked myself, okay, what is the supervisor left to do? And what is the information that is needed in order for this person to perform this task, this supervision task? This was also done through a cognitive task analysis, which led to a new performance requirement. And finally, here in gray on the right, I asked myself, based on what criteria will this supervisor decide to take over manually? Again, I performed a cognitive task analysis with this as a background material, leading to a performance requirement. So what are then these information needs? I can give you a very simple example. I mean, you've seen the size of the Excel sheet, so there's much more to talk about. But for this purpose of this presentation, for example, a supervisor supervising such a system may want to know if the agent has detected all relevant objects, but also which objects form a collision risk. Not all vessels that are in the area perform a collision risk. So a supervisor may want to double check whether the agent has actually seen the objects and also determined which of these form a collision risk, but also maybe about the internal state of the system itself. So which sensors are available and used by the collision avoidance system, and if it is plotting and tracking any targets it has detected. Criteria for human fallback could, for example, be that targets are not detected by the collision avoidance system, the collision risk is not detected, or it's detected too late, or it's insufficient, or there is a more, let's say, a different type of warning, like a request to intervene. The system is saying to the human supervisor, take over manually, please. or there could be a critical alarm prompting the human to take over manually. Preliminary results and the next step. This paper presented an analysis which adapted and developed a framework for developing performance requirements, and it was about identifying key task steps, key information needs, and criteria for fallback. Further work should focus on developing these specific information requirements to convey internal states, so transparency, such that transparency requirements can be developed, such that a supervisor can be able or is able to see into the automation. This is described in the paper. I encourage you to read it. Thank you for your attention. I'd be happy to answer any of your questions. Thank you.
Thank you so much, Koen. Okay, so he's there. Is there any question to him from the floor? Koen, if you're okay. So
yep.
I forgot the word. Can you go back to the slide? I think it was the...
It will be difficult for me to go back to the slide since it was actually a recording.
Sorry. Well, I think there was a system. So there was artificial intelligence. There is a system. So
yeah.
So how they are actually just communicate. I mean, I'm not really sure this is a kind of good question, but so there is an operator, there is artificial intelligence, there is a machine. So how do they, how the machine inform the operator you are doing something wrong?
Yeah, exactly. So in this case, I envisioned this situation where we have an agent. Let's just call it a collision avoidance system that's situated on the vessel that is has the capability to perceive its environment, to analyze this information, make decisions, and then implement these actions. And in this specific example, I've assumed that the supervisor, let's say the navigator, is present on the vessel or maybe even on the bridge, and is able to verify what the system is doing. Now, I haven't specified in this analysis on purpose, actually, whether this will be let's say a screen on which this information is made available, but of course you can imagine that there will be some kind of interface that is there that allows an operator to supervise what the system is performing, and based on that information that is being presented, let's say decide whether intervention is needed or not. I think so. What this analysis has done is I've taken a bottom-up approach, meaning that I've mapped all these tasks that are part of collision avoidance based on the collision regulations, assumed that there was a system capable of doing this, and then taken the role of the supervisor and asked myself, well, what is it then that the human supervisor is then left to do, and based on what information is this supervision performed. And I think what at least I hope to achieve also in this research I'm currently performing is that by identifying these information requirements, that I'm able to let's say provide requirements for these agents for effective supervision, whether a navigator is on the vessel itself, or whether this person is remotely supervising this from a shore control center, for example, but at least trying to establish the criteria that allows a supervisor to assess the capabilities of this collision avoidance system, and thereby supporting the decision making of, shall I let the system continue its task because it's performing adequately, or I see that manual intervention is needed. That's the that's the idea of this agent transparency concept that I'm investigating.
So is it part of a machine learning algorithm as well? So when the supervisor find out something, and then based on the experience maybe applied, so it can improve the algorithm of this.
Yeah, that's a good point. That is outside of the scope, but yeah, you can imagine that. You can imagine situations where a supervisor decides to intervene, and of course it would then be interesting to know why this supervisor thought that intervention was needed, and maybe it's because of maybe because there's room for improvement for this machine learning algorithm, for example. Yeah, that could be an application. Yeah.
Thank you so much for interesting presentation. Thank you so much.
Yeah, my pleasure. Thank you.
Thank you.